Okay, so a small change of pace here, change of direction. I'm going to, as a sort of warm up back to Ian Mackenzie, who's speaking on Saturday, I'm going to talk a little bit about doing chemistry with muons. So, as a sort of outline of this short talk, I'll talk a little bit about muons and materials. I think that's very much going to be a recap of what you've heard earlier, and something about why we might want to do chemistry with muons, and very much what we might learn to make it worthwhile doing chemistry with muons. And then I'll finish off with a few examples, which, as I said, Ian develop, I'm sure, in much greater depth. So, muons and materials, I'm very much recapping what Francis said right at the beginning of today. So when we stop our muons in our material, we can end up, well, with at least two states, but broadly speaking, we end up with the bare positive muons, the diamond muons. And if we want to do some chemistry, hopefully we end up with this muonium state, this hydrogen radical. So it's a bound muon electron. It's an atom that looks very much like hydrogen, but it's actually got a muon at the centre of the nucleus. And the states often coexist, so you'll often get a fraction, certainly in the materials you're going to do chemistry with, you'll often get a fraction of both appearing, and you can't control what you're going to get, so you hope you get enough of what you want to look at. And that's often the first thing you're going to look at in the experiment, to make sure you've got enough muonium, which you're probably going to be using in the experiment to do something useful. So why might we want to do chemistry with muonium? Well, fundamentally, we can do chemistry with muonium because it's chemically equivalent to the hydrogen atom. So it's got a similar Bohr radius, similar ionization energy, and similar reduced mass. So, as I'll show you later, everything that works with the hydrogen atom will actually work with muonium. But as I said, it's got the muons stuck as in the centre as the nucleus rather than the protons. So it's a light hydrogen atom. So it greatly extends the isotopic mass comparison. So it's roughly a 9th compared to hydrogen, and 18th compared to the deuterium, a similar atom with deuterium at the centre. So that's a very useful property. And then finally, if you're using muonium, you can work at high sensitivity. So instead of, say, with NMR, where we're looking for the nuclear, the free induction decay, the nuclear induced signal, now we can measure in high sensitivity because we're looking for the positron decays. So that means we can work with very dilute systems. So as I said, it's chemically equivalent to the hydrogen atom, so muonium will undergo all the same reactions as you might expect the hydrogen atom to go. So addition, as I'll come back to later, abstraction, radical recombination, electrotransfer, they should all work in the same way, but with due regard to the muonium atom being a light version of the hydrogen atom. So just focusing a little bit on addition reactions. So in addition reactions, you've got some molecule that you're interested in studying, and it's got this carbon-carbon double bond, and typically muonium will add across this bond to end up with some delocalized electron spin density across the molecule. And that gives you some hyperfine coupling as a mu and AP, and that makes for an extremely sensitive probe species that you can then go on to use and study, as I'll show you later. So there's only point in doing muonium chemistry if we're going to learn something. And broadly speaking, I think there's 4 areas where the subject's contributing. So reaction rates is a fairly big topic that people are looking at. Molecular structure, molecular dynamics, and molecular environments. All these things people have come along. They've used muons to do chemistry experiments to augment other studies that they're looking at to work in these areas. So what I'll do now is just very briefly show you an example of how people have used muon chemistry in each of these areas. So reaction kinetics. So people have looked at the reaction rate constants, K mu, and then gone on to determine activation energies for reactions. Both of those can easily be investigated, very easily investigated with muonium. And there's an example I've put in here with muonium chemistry, with the formation of the cyclohexadiene radicals, so essentially the addition of muonium onto the benzene ring. And you can see that isotope effects are visible both in K mu and EA immediately, so there's a clear purpose for doing this. And I was gratified when I went to a gas kinetics conference to find people talking about muonium as a matter of course, that this was clearly a useful code to them, and where they could make isotopic comparisons and then go on to test their calculations accordingly using this extra probe. Molecular structure, in this case we're looking at muonium addition onto a C60 molecule, and then people can then you can use avoided level crossing to look at the electron spin density across this molecule. So you can run your ALC experiment, you get resonances according to the various states you've got, and then you can, probably with a great deal of computational help, turn that back into some sort of map of the electron spin density on the molecule. In molecular dynamics is a nice example of this, of molecules tagged. So in this case, we've got benzene in a zeolite cage, and it's been tagged with the muon. So we've again formed the cyclohexadiene radical. And you can see from the calculations that the line shape is very dependent on the type of motion you've got. So wobbling, axial, and so forth give you a slightly different line shape and slightly different proportions of these two transitions that you'd expect in the avoided level crossing measurement. And then they can, of course, take experimental data and tie the calculations and experiment together. Finally, molecular environment. This was an experiment that was done here, looking at solvent effects. And again, we're looking at benzene, and in this case, we're looking at benzene dilute aqueous solutions. So again, we're putting muons in, we're forming radicals, so that this is the neat benzene. And you can see it splitting due to the coupling to the neighboring proton on the ring. And then if you move to 5 millimolar benzene in water, you can see there's a shift in the hyperfine coupling. And you can relate that shift to other measurements of solvent effects, and look at how the hyperfine interactions might be modified by the benzene molecule being surrounded by water molecules in the system. As I said, that's just a very quick overview. So Ian will be talking all about this, and I'm no doubt a great deal more during his lectures on Saturday morning.
So I do have a question. Normally, the electron from muonium comes from the sample itself. So my two questions would be, wouldn't that be a bit of a strong distortion to the material because you effectively have to take an electron from it? And is it possible to actually put an electron with the muon before it hits the sample?
Well, I think the answer to the second one, I mean, I suppose that's in some way a measure of some of the low energy muon, because you end up with emission of muonium from surfaces. But no one's ever used that in a real experiment, so I think that would be extremely difficult.
Okay.
Extremely difficult to do. I think the second part is, yeah, I mean, when, as Francis was saying at the start, you liberate tracks of ionized particles, but your muon often stops well beyond that track.
Okay.
So I don't think that's going to be an issue. And certainly in the chemistry application, you're forming muonium and then you're looking at the reactions that happen with that muonium species. So I think that's even more moving from anything that's going to
Thank you, that is.
affect the tracks. Yeah.
Anyone else?
You talked about quite a few small molecules in the talk. Is there a limit to the size of the molecules you can study?
No, I mean you can in principle work with any size molecule. Of course, it gets more difficult. Understand? I mean, if you look back at these, I mean, our interpretation of these things is key to knowing where the muon is added on the molecule. So with the benzene ring, you know that very simply where it's going to be. Now, if you've got a very large molecule with lots of potential efficient sites, you're going to have to do some work to find out where it's added, so you can understand what it's going to tell you, what it is telling you. And that's where many of the computation techniques come in, which we'll, I think, talk about later on in the course, but they become very crucial.
Right, thank you.
Anyone else? If not, then thanks to you.